Mr. B. Dhanasegar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. We are studying the theory of computation subject. So, in the previous episode, we have seen that is how we are converting the given context-free grammar into its equivalent Gribak normal form. So, two kinds of normal forms as far as context-free grammars are concerned. The first one is Chomsky normal form and the second one is Gribak normal form. So, in Chomsky normal form, the rules are of the form A derives BC or small a, that is two variables on the right hand side or a single terminal, and in Gribak normal form the rules are of the form A derives A alpha, where the right hand side is strictly required to start with the terminal, and as we start with the terminal, then the number of steps required for recognizing a string of length n is exactly going to be n. So, we can recognize a string that is much faster provided if the grammar is in Gribak normal form. But we can think about the Gribak normal form and the Chomsky normal form only if the grammar is having only useful symbols, that is all useless symbols have been eliminated, and the next one is the grammar should not have any kind of epsilon protections provided the languages does not include epsilon, and finally there is no question of having unit protections. Also the that is the left recursion available in the grammar is expected to be removed. So, after doing all these things, we are able to find out the that is grammar in Gribak normal form. So, that is what we had seen as far as the previous episode is concerned, and today we are having the closure properties of the context-free grammars. So, first we should know what is the meaning of the closure properties. Like normally the grammar once we have written, that is actually we will not be able to come up with a very complex grammar in the start itself. So, we will write the grammar in phases, that is first we will write for smaller languages, and then we will that is combine smaller languages to produce the larger languages. Maybe we will be writing the that is rule for our context-free grammar first of all for an expression, and then it will be extended for an assignment statement, and then after knowing the assignment statement we will think about for a that is something like a loop construct or an if statement. Then we will write a new rule which recognizes two statements at a time, that is like an assignment statement or it could be an if statement, like that. So, we will combine the languages to produce the larger languages, and finally it is for the entire program we will be having the grammar and with only one start symbol. So, there will be we will be having entire grammar together with the start symbol, so that this particular start symbol will be capable of recognizing that is the entire program. So, now the question is, how do you build a very complex grammar from the smaller things, or how do you recognize a very larger language by using a grammar? So, that is what we talk about the closure properties. So, how we will build that is larger languages or larger grammar from the smaller one with the help of some kind of operators, like we know that is how we are taking the union operation and how we will go for the concatenation operation. Certain operations which are compatible as far as this particular context-free grammars are concerned, and at the same time we can't claim that all operations are going to be compatible. Now, we need to find out what are all the operations compatible with the context-free languages or context-free grammars and what is not. So, with the help of some examples, and how do you do those operations which are actually compatible with context-free grammars. So, we will see the listing of the operations. The first one is which are closed, like we have union, that is the union of two different context-free languages, it is going to be closed. That means the new language is also going to be a that is context-free language. And the next one is going to be the concatenation, where we have two grammars and their respective languages are also known, and by doing the concatenation of those two languages, we have to prove that still we will be having a language which is the context free language. And another one is the reversal operation. The reversal in the sense like language which reads from left to right or from the right light. That is, if you are able to have a grammar for reading from left to right, and certainly it is possible to have a grammar for the same language provided it is read from right to left. That is called reversal. And finally, the closure. So it means that as a language, when it is repeated there is any number of times, still it is going to be a language in the form called context free grammar. So these are the operations which we have to study, that they are all going to be accepted by the context free languages. First, let us take the very first operation, that is union. See, union is going to be a binary operation. So there is a need for two different languages. We can call them as L1 and L2. So first of all, you should know that both L1 and L2 are context free. So this is about that is learning the union of two context free languages. So the languages you have taken should always be the context free languages. Then only we can talk about that is their operations or closure operations. So you are given two number of languages. One is L1 and another one is L2. Both are context free languages. To claim that they are context free languages, we should prove that they are having their own the context free grammars. So L1 has its context free grammar and L2 has its context free grammar. Let us assume that there is a grammar called G which is to be that is obtained, and the language to be constructed is L1 union L2. So how we will be constructing that language is, actually the resulting language is going to have either a string from that is L1 or a string from L2. So the grammar being used for the language L1 is going to have a start symbol called S1, and the grammar being used for the language L2 is going to have a start symbol called S2. And this S1 is a start symbol for any string recognized from L1. S2 is start symbol for the for any string recognized from the language called L2. So with that we know that the S1 is a starting symbol for a context free grammar, and the S2 is also a starting symbol for the context free grammar. So now the need for us is constructing a grammar which is going to be a context free grammar, but it will recognize the new language L1 union L2, that is either a string from L1 or a string from L2. So we have to find out what are going to be the four components. The grammar has four components normally: the variable set, terminal set, production set, and the start symbol of the grammar. So here the variable set, already we are having that is the variable set of your that is the grammar called that is grammar for L1 and the grammar for that is L2. So it is going to be your V. V is having the variable set from that is L1, the grammar for L1, and the variable set from the grammar for L2. So in addition with that, we will be introducing a new variable called S. Actually that is the variable for which we need to write the productions. So we need not bother about writing productions for the remaining variables available in the grammar, as they are simply taken from the grammar for language L1 and the grammar for language L2. So it is going to be the union of all the variables available in the language meant for L1 and all variables meant for the language L2. In addition with that, we will be introducing that S. So this is what your variable set for the new grammar. And as far as terminal set is concerned, the terminal set T includes all terminals from the grammar meant for L1 and all terminals from the grammar meant for that is L2. That is about your terminal set, because we should have both there is terminals in L1 and L2, since the string can be recognized either from L1 or from L2. So to recognize a string from L1, we must have all terminals from L1, and to recognize a string from L2, we must have all terminals from that is L2. So now regarding the productions, already we have some set of productions from your that is the grammar that is for L1 and for L2. So that set, that is your production, that is union of productions from L1 and productions from L2, it's all already there in P, that is what the set of our productions, and we need to have an additional production for this new grammar. So that production is returned for the symbol which you have introduced here. The variable which is newly introduced here is S, and what the purpose of this S is, it is actually for connecting the start symbol of the first grammar and start symbol of the second grammar. So S derives S1 or S2. So we cannot have the concatenation of both, because the language itself is saying that either a string from L1 or a string from L2. So if you want to generate a string from L1, then the first step in the derivation of that string is S derives S1, and if you want to have a string from that is L2, then the first step for the derivation of that string is going to be S derives that is S2. So now we want to have the new rule S derives S1 or S2. So the productions include that is P union S derives S1 union S1 or S2, and the very last component is what is going to start symbol of the grammar. The start symbol of the grammar is S. So now we have all the four components. The variable set is V union S, terminal set is the terminal set from the first grammar union terminal set from the second grammar, and the production set is productions from the first grammar union production from the second grammar union S derives S1 or S2, and start symbol is the newly introduced variable called S. And you know that S1 is start symbol for the first grammar and S2 is start symbol for the second grammar, which are meant for actually the language L1 and called the language L2. So now we have the context free grammar which is called G, which is capable of recognizing the language called that is L1 union L2. So we can claim that the union operation is closed, means we will be having the new language which is obtained as a result of the union of two languages. So now let us see that is how we are proving that the context free grammars or the context free languages are closed under concatenation. First of all, concatenation is also going to be a binary operation which needs two different languages, both L1 and that is L2, and already L1 is a context free language and L2 is also a context free language. If both L1 and L2 are context free languages, their corresponding grammars are also available. So now we need to find out what is the context free grammar meant for the concatenated language. The language concatenated is L1 dot L2, L1 that is dot L2, that is a string from L1 followed by a string from L2, that is both are taken together. So this L could be possibly empty, or even L2 could also be empty, but even both could also be empty, but the order is very important. So you take a string strictly from L1 first and followed by a string from L2. So L1 that is followed by L2. So now the question is, how do you find out the language which is obtained after the concatenation? So we will go for constructing the new grammar G with all the four components, that is V, T, P and S start symbol. So G is equal to the first set is going to be the variable set. So it is going to be V union S, where V is the set of all variables from the first grammar and from the second grammar. Then S is a newly introduced variable for the new grammar which is meant for recognizing the concatenation of two different languages. So it is going to be S, and next it is going to be the T, that is going to be the terminal set from the first grammar and the terminal set from the second grammar, and the third component is going to be list of all productions. So we have P, it means all productions from the grammar 1 and grammar 2 union. So what is going to be the new grammar now, or new production to be written along with this particular grammar, so that we will be able to find out that is the new grammar that is obtained for concatenation. So in the previous case, like when we were trying to find out the union of two different languages, we had a production called S derives S1 or S2. But this time we want to take a string from the language S1, that is L1, and immediately followed by that we want to take a string from that is language called L2. So there is a need for introducing S1 and S2, but in the same order. So S1 immediately followed by S2. So the meaning of this production is when we expand the start symbol, that is S, with the derivation which is right hand side called S1 followed by S2. So, we need to recognize a string from S1 by using the appropriate rules available in the grammar called G1, and then expand this S2 to generate a string from the that is language called L2. So, it is needed that first string from there is S1 and second string from S2, it is nothing but the concatenation of both S1 and a string from L1 and a string from L2. So, now finally, there is going to be the start symbol of the grammar, which is going to be your S, that is new grammar symbol introduced as far as grammar is concerned. So, once again we find that we are able to successfully construct a that is a context free grammar which is meant for recognizing the concatenation of two languages. It is a language L1 and a language called L2. So far we have studied that is how we are proving the language union or the union of two languages and the concatenation of two languages are closed under the context free languages. After a short break, we will continue with more number of operations. Welcome back. We have seen that is how the union of two different that is context free languages are closed, and similarly how the concatenation of two different languages are closed. And we are going to see another that is operation which is the reversal of a context free language. That means you have a string called ABC, and if you have a grammar for recognizing ABC all terminals, and there should be definitely a grammar for recognizing even CBA also. So, CBA is exactly the reverse of that ABC. So, having a grammar for the language ABC, it should be there should be a grammar for even CBA. So, then we can claim that the reversal operation is also going to be a context free language, or it is accepted by context free and that is grammars. See, to have that, it is going to be a unary operation now. So, you will be taking only one that is language L1, and there will be some number of strings available in the language L1, and we are going to first of all define what is going to be the reversal. So, the reversal is if you are having that is A derives that is alpha. So, now what should be done is we will be writing the reversal of A, that is A derives alpha reversal R, that the superfix R, it says that the reversal of A. So, for example, if I have a production like A derives B, C, D, then we will be introducing that reversal of B, C, D as D, C, B. So, if I am having A derives B, C, D, then I will rewrite the production as A derives D, C, B. So, that there is earlier we had a string derived from B and then followed by a string from C and followed by a string from D. Now, since D is the first symbol available on the right hand side, we will be having D, a string derived from D, then followed by a string derived from C and followed by a string derived from B. So, that we will be able to claim that the language is simply the reversal. So, now to look it into the closure, it is a very important that is operation that is context free languages, for context free languages or even for regular languages. How do you find out the new language which is obtained for that is closure? So, here we have the unary operation. So, it is going to be only one language, we take it as L1, and now for the context free grammar which is denoting the closure of that L1 is going to be that is defined in this following way. That is, once again we will be having the new grammar, and there will be 4 number of components: the variable set, terminal set, production set, and even the and finally it is going to be the that is the start symbol. So, one important point which we ought to remember here is the closure of a language will be definitely including epsilon, because closure includes 0 times of any language. When it is going to be 0 times of any language, then irrespective of whatever be the alphabet, that is whatever be the terminal set, there will be a string called epsilon. So, avoiding completely the epsilon production from the grammar is certainly not possible, as we include epsilon as a string of the language. Okay. So, now we shall see that is how we will form the various that is components of the grammar. So, the first one is going to be the variable set. So, V, which is taken from the variable set of the given grammar which is meant for the language called L1. Then union, that is S. So, S is going to be the start symbol of the grammar, which will be the new symbol for which we need to write the new grammar, new production. Then terminal set, it is simply copied from the terminal set of the language which is given for us, for which we need to find out the closure. And then P, that is going to be the list of all productions. So, the productions P includes all productions from the given grammar, that is P union, and we will write now one more rule which will be generating the closure of the language. First, you know that what is a closure? It is the 0 times or 1 time or any number of times of the given string. If it is going to be 0 times of any string, then we want to have a straight rule, that is S derives epsilon. So, that is what this rule has been introduced. S derives epsilon is there. This will ensure 0 times of the language, that is a part of your closure. And suppose if you want to have exactly one number of time, then we will go for the first rule, where we have an expansion called S derives S1S, and S1 is going to be the start symbol of the given language. So, that will generate any string from the language L1. So, you are leaving that is the string recognition by from that is L1 to S1, it is done, and we know that there is another variable called S is there. So, if you are concerned about only one time, that is the string from that or L1, then this S could be simply replaced by epsilon using the straight rule for S. S derives epsilon. So, in that case your S will be expanded to that is exactly S1 once. So, we will be having one time of the given language called L1. And suppose if you are interested in that is expanding this multiple number of times, then we have to expand the rule S derives S1S as many times as we wanted to have. If you are interested in having 3 number of times of this S1, then first one it is going to be S derives S1S, second time this S will be expanded to S1S, and third time once again this S will be expanded to S1S, and the fourth time this S will be expanded to epsilon, leaving S1, S1 and S1, and each S1 will recognize a string from the language called L1. So, you will be having the concatenation of S1 3 times, that will give you 3 times of the language called L1, that is going to be your closure. So, this is also a context free grammar, since we are able to successfully find out all the 4 components of the context free grammar. So, we can claim that even closure is also closed under the context free languages. So, now we have to look into the intersection operation. So, this is an operation which is not going to be that is accepted by the context free languages. So, we have 2 languages L1 and L2, and now the question is now whether the intersection of the 2 languages will be giving always into that is context free languages or not. As long as the language is finite, like for example your L1 is finite and L2 is finite, then we are very sure that even the intersection is also going to be a finite that is language. Every finite language is regular and every finite language is context free. So, that part we have already studied. So, if when we have the finite languages, there is no need of proving that these languages are going to be that is accepted by intersection or not. So, now the question is when we have 2 different that is languages, both are infinite in nature, and the resulting language is also going to be infinite. Now, there is a need for looking into whether the concatenation that is intersection of these 2 languages which are infinite are going to have the context free property or not. So, we will prove this with the help of an example, and finally, we conclude that the intersection of 2 context free languages not necessarily be context free. So, let us take 2 different languages. The first one is L1 is 0 power n, 1 power n, 2 power m, and n and m are greater than or equal to 1. It is a context free language. You can understand what is happening, what this pattern conveys. It is 0 power n followed by 1 power n followed by 2 power n. That is, the number of zeros and number of 1s are going to be same, but whereas the number of 2s not necessarily be related with zeros and 1s. That is the first language. And the second language is we have 0 power m followed by 1 power n and 2 power n. Once again n and m are greater than or equal to 0, it is another language, and it is possible to come up with context free grammar for these two languages. As far as the first one is concerned, we can now that is a derives bc, and b is going to be of the form that is 0 power n followed by 1 power n, same number of ones and zeros, and followed by c can have any number of 2's. That is your first part. And the second part, we will be having a derives bc, where b recursively generate as many zeros as we wanted to have, and c will ensure that 1's and 2's are generated in equal number of times. So, it is possible to have grammar for both L1 and even for L2, and now we have, so we can claim that both L1 and L2 are context free languages. So, now we can think about what is going to be the there is your intersection language. It is going to be your L1 intersection, that is L2. So, when you take the common strings among these two, strictly we want to have, we will be having strings of the form 0 power n followed by 1 power n followed by 2 power n, because here we have 0 power n and here we have 0 power m. So, that is the difference, and here we have 2 power m and here we are having 2 power n, that is as a difference. But when you take the common strings, it is strictly required that the number of zeros, the number of ones and the number of 2's are going to be same. That means the intersection language of L1 and L2 will be having, that is 0 power n, 1 power n and 2 power n, where n is greater than or equal to 1. And this language is not going to be a context free language, because of it is no way, that is we can even use the pumping lemma for proving this language is not regular, which we have already done. So, since we know that when there are two number of components which are related in terms of the count, we can recognize them with the help of a PDA. But when there are three number of components which are supposed to be related, it is certainly not possible with the help of a push down automata or a stack for recognizing the pattern of the form 0 power n, 1 power n and 2 power n. So, it is certainly not possible to construct a context free grammar for that. It means this particular language is not going to be a context free language. So, if you are trying to construct a grammar for this, we will definitely fail. So, we can't claim that. Actually, this language is obtained as a result of intersection of two context free languages. L1 is context free, L2 is also context free, but the resulting grammar we are getting, the resulting language is going to be 0 power n, 1 power n, 2 power n, which is not going to be context free. So, that concludes that the intersection of the two different context free languages not necessarily be context free, and strictly this rule is not applicable for finite languages. As far as finite languages are concerned, even if those languages are obtained as a result of the intersection of two context free languages, no problem, certainly we will be able to come up with the context free grammar for that. But when the language is infinite, we must ensure that whether there exists a context free language or not, so intersection not necessarily be, that is accepted by context free languages. To have more properties, like the first one is, so if L is a context free language and R is a regular language, then we can take about the intersection of that L and R. In that case, definitely the language is going to be a context free language, but one condition is the second argument is not a context free language, but it is going to be a regular language. We are very sure that the language is going to be the context free language, so that we can even prove with the help of constructing a grammar which will be recognizing the context free language and it is regular language. And L minus R, that is, it is saying that strings available in a context free language and strings available in a regular language. So, the difference is all strings available in L but not in R. So, we will remove some of the strings from that L, but still all strings available in L are going to the strings only available in L are going to be the resulting strings. As already L is context free language, so L minus R is also going to be context free language, and the complement of L is not necessarily be context free, because of if we find that complement is context free, then it is possible to prove that intersection is also going to be that is context free, as we find that the intersection operation can be replaced by a union operation by the complements. So, that is what we know, that the complement of context free language is not necessarily be context free due to the intersection is non context free. And the last one is going to be, that is L1 minus L2. So, we have already seen that L minus R is going to be a context free language, and here it is going to be L1 minus L2, that is the set of all strings in L1 but not in L2. Once again, this could also be, that is implemented by using the intersection operation or the complement operation, since we know that intersection is non-context free and complement is also non-context free, we will be able to conclude that L1 minus L2 is also not going to be a context free language. So, that is about the properties of your that is context free languages. So, to summarize, we have seen the union, then concatenation, then reversal and the closure. These are the operations which are accepted by the context free languages. That means that they are going to be the context free. But whereas we have seen one operation, that is the intersection operation, which is proved as non-context free operator, that is it's not accepted by context free languages, and we have given the proof with that is example, proof by example, taken two different context free languages, and we have computed the intersection of that context free language, and that language is a non-context free language, so intersection is not accepted. So, that is about the summary. The questions component, you may be asked to prove the context free languages are closed under union or but not the intersection, and they are reversal, that is accepting the reversal operations, and can the difference between the two context free languages become the context free. So, the difference between two context free languages is not going to be context free, whereas the difference between a context free language and a regular language is going to be context free. So, that is about the question components. So, with this I conclude this episode. Thank you all.